Hello, my name is Marcel Müller and I have the honor to present you our most recent work about tomographic single-shot time-resolved laser-induced incandescence for soot characterization in turbulent flames. I would like to start with a short literature review about tomographic soot characterization via LRI as a motivation for this work. The first one is from Terry Meyer et al. From 2016, and they measured the soot volume fraction in a turbulent flame, and this was in fact a 4D LRI measurement, as 3 dimensions were the spatial dimensions and the fourth was the time domain. This was a single shot measurement and they did this with 7 intensified high-speed cameras. The second one is from Ellis Hall from 2020. They measured the particle size in a turbulent flame and used the assumption of a constant temperature over the whole flame. This was then a 3D LRI measurement and also a single shot measurement with 3 ultra high-speed cameras. The last one is from Florian Bauer et al. From 2021. They measured the particle size and the temperature in a laminar flame. So as this was a laminar flame, they only needed 1 intensified camera for this. And this in fact was also a 3-dimension LRI measurement. And now we want to combine all those 3 works as we want to measure 3 quantities simultaneously: the soot volume fraction, the particle size, and the temperature in a turbulent flame. This is also a single shot measurement in the end and can be called a 3D LRI measurement. So let's go to the theory. How does LRI, so laser-induced incandescence, actually work? So here you see a soot particle and a detection system, in this case a camera. We have a short laser pulse which will heat up our soot particle, and therefore we have an elevated temperature from the surrounding. And after the pulse passes our soot particle, this particle will cool down to the surrounding temperature. And this can be described with the change of internal energy with time. And multiple models to describe this are available. And we only use 3 heat flux models as they are the most important ones for our case. And this is absorption, conduction, and sublimation. And this is how such LII signal curves look like for different particle sizes. And you see that smaller particles cool down faster as larger particles. So how do we get our wanted quantity of interest? The particle size. And we can measure it pointwise. So we use, for example, photomultiplier tubes, and there we measure this decay and then can fit it to the model. And from that we can get our desired particle diameter. But if we want to do it in an imaging way, so 2D or 3-dimensional, we only have 2, maybe sometimes more time instances to compare it with the model. But as you see here, it's enough. So here it is normalized to the first point, and you can definitely discriminate between the different sizes at the second point. And all those curves you see here are for one initial temperature. But if we look at a different temperature, so here the dashed lines, you see that a solid and a dashed line coincide, which means that it's really crucial and you need to know the initial temperature prior to your laser pulse to obtain absolute values of the primary particle size. And that's why we also have to measure the temperature prior to the laser pulse, which we do with the measurement technique two color pyrometry. And here you see the spectral radiant emittance of soot for different temperatures and also the formula to compute that. And now we only use 2 wavelengths. And if we calculate the ratio of those 2 wavelengths, we can get such a lookup table. So this ratio is temperature dependent. If we calculate it for different temperatures, we get this lookup table. And now we do this also for our measurements, which we have to correct with a calibration factor, which we obtain from a calibration measurement, and then go to this lookup table and get our desired temperature. That's enough theory from my side today. Now let's go to the experimental setup, which in our case consists of 4 parts. The first one are the used burners. So we use two diffusion burners. The first one is a laminar burner, well-known Gilder burner, which we mainly use only for calibration and verification purposes. The second one is a weakly turbulent burner, which produces a flame with a flame height of approximately 250 millimeter. And both burners are centered here in our setup so we can exchange them. And here you also see the second part of our setup, which is the beam forming and evaluation. So as we want to measure in 3 dimensions, we need to irradiate the flame volumetrically. And for that, we have to expand our laser beam, which we do with 3 lenses. And after the beam passes through the flame, we capture our laser beam with a beam profile camera and also measure the energy of this laser shot. And here you see how our beam profile looks like. So we have an elliptic shape with a beam profile size of 12 times 40 millimeters. And we have an average laser energy per pulse of 569 millijoule. The third part, as we want, as I said, perform tomographic measurements, we need different views of our object. And for that, we use in our case a so-called fiber bundle, which has in our case 8 inputs, which coincide to 1 output. And this is how it looks. So if you place, in this case, we place the target perpendicular to view 5. And then at the output, you see all 8 views at the same time simultaneously. And now to our last part, the acquisition. We need 4 intensified cameras to measure all of our 3 quantities of interest at the same time. And as intensity is crucial, we used a combination of dichroic mirrors and bandpass filters to get an optimized signal intensity at each camera. And the first 2 cameras are for the measurement of 2-color pyrometry, so measurement of the temperature. We used a bandpass filter of 850 nanometers and 475 nanometer on those cameras. And for the LI cameras, which capture the signal decay at 2 time instances, we used a 600 nanometer bandpass filter. So they share this bandpass filter because it's placed in front of the beam splitter cube. So now, how do we actually get our quantities of interest? So the starting point are the 2D images of our 4 intensified cameras. Then we have to process those 2D images. So we have to subtract dark current and apply a flat field correction, for example. And then we can go from 2D to 3D by doing the reconstruction, where we used a ART algorithm, and this results in a voxel size of 200 microns in each direction for all of our cubes. Now we can calculate our first quantity of interest, the temperature, by just building a ratio of our signal intensity cubes from the 2-color pyrometry cameras. And I already explained how it works in the theory section. The next quantity is the soot volume fraction. And this one we compute by using the temperature cube and one of the signal intensity cubes of the 2-color pyrometry cameras. By doing that, we only get relative values for the soot volume fraction. But if we couple it with an extinction measurement, which we performed at 42 millimeters height above the burner in the laminar Gilder flame, and also neglect influences of scattering, we get absolute values for the volume fraction. So only one quantity is missing now, but for that we need an additional information, and this is the fluence. And we get this from the beam profile image from the beam profile camera and propagate it through the flame. And we also use the volume fraction cube because we account for absorption of the flame of the laser beam. And with the 2 LI intensity cubes, the temperature and the fluence, we can now calculate our primary particle size. In the box below, you see some values we used for the modeling of the signal decay. All right, so now in theory we have everything we need for our results, but we want to verify if this approach is valid. And for that we go in the laminar Gilder flame, where the reference position at 42 millimeters height above the burner is well known. And there are a lot of literature values available for this position. And you see them here in the second column. They are extracted from Schulz et al. From 2006. And in the third column, you see our values. And we get our values by placing a sphere with a diameter of 1 millimeter in the center at 42 millimeters height above the burner and calculate a mean value of those voxels inside and also an uncertainty by computing the standard deviation of those voxels inside. And if you compare our values to the reference, you see that they match really well. So now let's go to the actual results, the three-dimensional results of the turbulent flame. You see here our three quantities of interest, and we achieved a great recreation of the flame shape. We can identify fields where, for example, higher temperatures or more soot is present. We are also able to visualize multiple magnitudes for the soot volume fraction. And you may have seen that our particle diameter cube appears a little smaller than the other two. And this is due to the fact that the beam profile is actually smaller than the flame size, and that's why it appears smaller. And you can actually see our profile shape, this elliptic shape. For example, now you can see this elliptic shape, and in 180 degrees later you see it again. And now the question is this the perfect way of visualization? So for example, if we want to do some correlations between our quantities of interest, it's maybe a little bit hard to do this with this kind of visualization, and that's why we came up with a different way. So we cut out a small part of the flame, so in this case 5 millimeters in height of the flame for all of our three quantities, and then count how often a combination in discrete intervals occurs in this cutout section. And you see here the intervals below the plot, and this is the result. So you get such a point cloud, and if you perform here a marginalization on those data, which is just a projection in one direction, and here you can already see some correlations between two quantities, and we can do this in every direction, and this is how it looks like. And now one projection is a joint probability density function in the end, and there we can extract isoprobability lines, and we did this for three probability levels, so 75%, 50%, and 25%. And that means that, for example, 75%, that 75% of the combinations lie inside of this blue line. And this is just for one single shot. And we can also draw a second one or a third one. And in the end, we had 12 single shots. And here we can, for example, extract how much our object fluctuates. So, for example, for a perfect laminar case, we should only see 3 lines, so 1 line for each color, because it doesn't matter how many shots we take, they should be all the same, they should coincide. And what we also can do is to plot this for several heights. So if you focus on the first column, for example, and go from 18 millimeters to 100 millimeter, you see that the center shifts a little bit to the right, which means that we are still in the regime of particle growth. And in fact, with our measurement and visualization technique, we are able to perform a comprehensive characterization of soot in turbulent flames and also supply measurement data which can be used for validating simulation data. With that, I now want to summarize my presentation. We used a fiber bundle in our tomographic setup to reduce experimental effort for 3D LRI measurements. We first verified our approach on a laminar Gilder flame, and to our knowledge, this is the first multi-parameter single-shot LRI measurement in 3 dimensions. And with the presented setup, a comprehensive characterization of soot formation in a turbulent flame is possible. In a next step, we want to measure our quantities of interest in 4 dimensions, which will be then a 4D multi-parameter single-shot LRI measurement in a turbulent flame. For that, we need to upgrade our equipment first so that it is capable to measure with a repetition rate in the kilohertz regime. And with that, we are then able to visualize and follow areas of soot growth and oxidation processes in a turbulent flame. And with that, I want to end my presentation. Thank you very much for your interest.